Okay, thank you very much. Thank you for the detailed introduction. And thanks for the invitation to this very important seminar. So I'm now in Europe because last week there was a EarthCARE pre-launch workshop. I'm wearing a EarthCARE polo shirt like this one. This is the EarthCARE logo. So all the attendants to the workshop are wearing this polo shirts. So my role today is to know you, the EarthCARE, and the importance of the EarthCARE satellite and how this affect modeling community. So this my research today is Shuhei Matsugishi here and Usaburo here collaborations. Okay, I'll start. So the first. Okay, first I introduce the EarthCARE. What is EarthCARE satellite? The launch schedule is announced last week. So this is soon launch, but I have been 18 years involvement this project. So this satellite is delayed so much. Difficulty of the instrument development. The important instrument for the modeler, climate modeler is CPR, Cloud Profiling Radar. This is something similar to CloudSat, cloud radar, but the new sensor observing the Doppler velocity. So it's vertical pointing and observe the vertical velocity of mainly the cloud sedimentation speed, precipitation speed, but sometimes we hope to capture updraft of the convection. So, and also LiDAR, radiometer, and the imager. These four sensors, cloud and aerosol and radiation energy project satellite. So please, first of all, please remember this satellite will soon launch, and it's very important for the climate community. Okay, so we have been for more than 10 years. My main area of the high resolution kilometer scale modeling and satellite collaboration. To do that, we have created EarthCARE-like data by the simulation using the kilometer scale model. In that case, 3.5 mesh NICAM simulation was used to create EarthCARE-like data using a simulator. We developed a satellite simulator called the Joint Simulator for Satellite Sensor. It's something similar to COSP, but is more, more comprehensive and consistent to the cloud and sensor assumptions. But this paper is introduction of paper is recently published, and the data is available. But this data is we have created 10 years ago, and this data is used for retrieval team and testing satellite handling. But we recently conducted much more high-resolution global simulation, 220-meter simulation. So we use this information for the EarthCARE-like signal to study the prepare for the soon launching. So this high resolution is itself useful to know how EarthCARE will look like, but it's also useful for the more popular kilometer scale model. We are doing the diamond type intercomparison, but this is a kilometer scale. So it's clarify the limitation and the usefulness of the kilometer scale storm resolving model by using high resolution model. Okay, we first introduce EarthCARE synthetic data briefly, then go into the details 220-meter simulation, and show the EarthCARE-like signal, but 220-meter global simulation, and for the preparation of the actual EarthCARE observation. And finally, we propose how to use EarthCARE data for the modeling, intercomparison, or evaluation. That's my structure of today's talk. Okay, EarthCARE synthetic data is something like the here. We conducted 3.5 mesh simulation for kind of limited period. And using this simulated data, we calculate virtual path of the satellite track and calculate for each sensor signals. So this data is used for satellite community before the launch, they can test the retrieval algorithm. So these are example of the imager for different band, and this is example of the cross section of the radar signal and Doppler velocities. And also we are testing the sensor characteristics. Okay, so these are existing synthetic data. Okay, so different topic. 220 simulation has been, we started this simulation 2 years ago. So currently, Shuhei Matsugishi conducted and developed the simulation using the Fugaku, supercomputer Fugaku in flagship computer in Japan. Using more than half nodes, we conducted this simulation. So this is a spec of the simulation. Basically, more than 50% is used in this model with mixed precision and huge data set output. So 220-meter simulation, we have we hesitatedly say large eddy resolving, mostly for deep compact motion. But as we show, for the shallow class, it's not still far away to resolving our convergence. And this model is can be a base for comparison reference for the more popular global kilometer scale model, and also good for the evaluation using the satellite, like EarthCARE and the field observation. Actually, intensive field observation is planned next summer, so we want to use satellite and field observation data for intercomparison. That will be, we'll come back again, the last slide. Okay, the motivation of the high resolution. We have done experience up to the 870-meter simulation 10 years ago. This is OLR difference. OLR is okay, almost similar around the kilometer scale, but the vertical velocity is changing. This is from 14 kilometer to sub-kilometer, 870 meter. Composite of the vertical and horizontal grid structure. Vertical velocity is changing, not converging. This is well known by the more basic simulation by George Bryan, around 120 meters vertical velocity is almost convergent. So we need much more high resolution. So that's why we targeted 200 meters. But to resolve, to capture more realistic vertical velocity. So this is our model set configuration of the set simulation. So we choose a different resolution. So and starting for the diamond summer intercomparison, that's August 2016. 1 week simulation for 3.5, and we started 1.7 kilometer simulation. Then we run the 440 meter and 220 meter simulation. The highest simulation we conducted 8 hours. This is something similar to the short range forecast by the regional model. Actually, JMA 2 kilometer regional model is run every day, kind of half a day. So it's some almost similar to the short range forecast. So we assume initial few hours are spin up and analysis for kind of 6 hours. Okay, these are resolution dependency OLR. OLR is very similar across these resolutions. So there is a tropical cyclone here and the ITC structure here. So, yeah, something, it's almost similar. But I think this is most clearly show the resolution dependency by precipitation. 3.5 simulation is here. Tropical cyclone IO structure is captured, but very strong isolated precipitation seen. And 1.7, 870, 1 to 40 meter, 220 meter. Of course, finer scale structure becomes visible, but the gradient, I mean, this smaller to larger precipitation contrast gradient can be becoming more visible around this resolution. 1.7 is okay, much better than 3.5. And maybe sub-kilometer, this kind of gradation is more visible. So I think this is an important point for the higher resolution. This is not only the precipitation area, but also the precipitation spectra, convective spectrum. I mean the different height of the convection and this different spectra of convection. So our target is vertical velocities and also the circulation kind of different level, multi-layer circulation. Okay, I'll show some of the basic statistics. The important and very difficult thing is the shallow class. We test in this kind of simulation, PPL scheme is important. One is LES type Smagorinsky scheme. The other is RANS, Reynolds average scheme, mean Yama's scheme. And maybe we think we move to LES type scheme if we go into higher resolution. Generally, Smagorinsky is higher, more shallow class. But unfortunately, if we go in high resolution, shallow class are decreasing. It's similar. This one. Okay, and this is precipitation statistics. Precipitation is changing, slightly reduced. And also the important order is similar, but the outgoing short wave is the bias. Even the 3 point, we have a smaller fraction, and it decreases. So this is a difference from the observation, even in the high resolution. Okay, this is almost 15 minutes. I think I will show briefly the vertical velocity structure. Vertical velocity structure, it's difficult to show because of different resolution. So we horizontal axis meter and height, so different resolution. So we may see the core area is similar magnitude around this resolution. But we classify the larger convection and smaller convection. In the larger convection case, this is almost becoming convergence sign, but structure different. So we feel something more, but tend to convective tendency, convergent tendency. And also relationship relative humidity in this domain, height, horizontal domain, this resolution becomes something similar to this corresponding to this one. So it's a good sign. Okay, we skip this complicated figure and briefly show, we calculate the area of precipitation area and show resolution dependency, show the 3.5 we have a kind of kilometer to 10 kilometer peak, but this peak reduced more flat or more higher, smaller scale precipitation is more ubiquitous on the very high resolution. So this is characteristics in the high resolution model precipitation areas. Okay, vertical velocity is, as I say, something getting convergent structure, but still not yet. So we have calculate mean velocity and maximum velocity. Mean velocity is smaller, maximum velocity is also become larger. These are characteristics. Okay, so the first part, but the main part is we have anyway conducted 220 meter simulation, and the precipitation gradient captured at around kilometer scale model, and the vertical velocity statistics we are becoming obtained. And we are now looking at large scale resolution dependency with large scale circulation. Okay, the main minutes, I'll show you how these are important for the EarthCARE. So we recalculate EarthCARE cloud profile radar-like signals for radar reflectivity and Doppler velocity, both. But the Doppler velocity, actually, we have a lot of observations in the ground basis. And toward that, we have this is 1 point observation in Japan, vertical pointing, radar reflectivity and Doppler velocity, height and velocity, different cases, typhoon cases and more relatively weaker rain cases. Generally, higher level ice is kind of this 0 to 2 meter speed, and the rain is this speed, 4 and 6 meters. And this does not change in different cases. And this can be roughly ice phase, rain phase, and also global phase, and upward draft phase. This kind of classification is easily obtained by Doppler velocity. And Doppler velocity profile is also obtained different, like wind profiler profile, ice rain phase. So this is well known from the observation case, but maybe not familiar to modelers because rain or snowfall speed are generally used for tuning parameter. But from now on, if we see the EarthCARE data, this can be used for constraint or observational value. So that's an important message we want to make. So before the EarthCARE, we calculate these signals using different resolution. This is 3.5, 870, I add 220 meter data. So this is signal and Doppler velocity. Global view of Doppler velocity shows a clear phase difference, liquid and ice. This is at the lower level, 3 kilometer. And upper level, more signals in the resolution, higher resolution, and almost ice phase. And the upward velocity is very sparse. If we use threshold 3 meters per second, very small fraction, and this fraction is a resolution dependency more for high resolution. So we should talk about this percentage for upward velocity, but we hope to capture some of the signals in the EarthCARE. So maybe we should calculate this kind of figure. Maybe the temperature in the vertical x-axis is much better. So the resolution dependency is very small. So this is very familiar, vertical velocity, Doppler velocity, ice phase, rain phase. And this is signal, similar to CloudSat. Something like a land-ocean contrast, we can see the resolution dependency. And the Doppler velocity land-ocean contrast can be calculated. So maybe this kind of diagnostic is important for the modeling evaluations. Okay, finally 220 meters behavior. Much complicated structure obtained and more upward structure obtained by the red. For the different levels, and the lower levels are attenuated, but the Doppler velocity is okay. So we should see, compare this. This is global like higher velocity ice and up liquid phase can be seen this kind of figures. Okay, I want to finish. We are looking at different LES scheme, PBS scheme, smuggling scheme, and Merayama scheme. So very dependent on the PBS scheme is this kind of resolution. And the cloud microphysics also this scheme is based on single moment scheme, but we also trying double moment scheme. Okay, thank you very much. We want to summarize. Following EarthCARE synthetic data by 3.5 kilometer mesh NICAM data, we update the data by the global 220 meter mesh NICAM simulation and using a simulator, joint simulator. We obtained global views and resolution dependent simulated Doppler velocity and radar reflectivity of cloud profiling radar with EarthCARE. Doppler velocity shows clear dependence on liquid and ice phase. Land and ocean content difference is detected. Resolution dependence of upward motion is also quantified. The simulation data is to understand the characteristics of the satellite, non-uniform beam feeding effects, and intercompression EarthCARE observation. So finally, we propose the intercomparison of the simulation using the EarthCARE. So our target is EarthCARE will launch next May, and the intensive observation called Orchestra is planned August 17th. So we plan the 40-day kind of more than 1 month simulation, like previous diamond type simulation. So we propose simulation and the ask using constraint of the Doppler velocity or other data, and it may ask the model improvement or comparison. Then we will have a different version, default version and the improved version, and compare the simulation result. So phase 1 and phase 2 intercompression is planned. Okay, I want to finish at this point. Thank you very much.
All right, thank you, Masaki. Now we will open it up for questions. We have some time for some questions, but I'll go ahead and feel free to raise your hand or ask it in the chat. But I'll go ahead and throw out the first one because I'm curious. I feel like I should know this, but it would be good since you've been using the data to understand. But the first question is, how does EarthCARE kind of expand upon what we've been able to do with CloudSat Calypso? So how does that, from a modeling perspective, how does EarthCARE enable kind of more modeling advances and building on CloudSat and Calypso?
Yeah, the radar band is something like CloudSat W band cloud radar, but the Doppler velocity is observed in the first time from the space. For the LiDAR is a high spectral radar, and the important point is the radar ratio is obtained. So the more finer categorization of aerosol is possible. That's two advantage of EarthCARE.
And I guess can I just kind of follow up then? How are those? And then how are those going to enable kind of those technological increases enable advances in the modeling? Do you think?
So sorry, what's the question?
How so? you said like the scattering ratio and the Doppler velocity are kind of unique pieces of information. So how will that, having that, how will that, I think you showed a lot about how maybe I'm asking you to repeat yourself, but you showed a lot about how having the Doppler velocity can be used in these evaluation metrics. Um, but I'll just ask my question anyway, which is how would those technological advances, you know, help specifically for advancing modeling?
Yes, that's right. That's an important point. So yeah, maybe most modelers don't know the observational basis because I didn't know. But there is a well-known characteristic of the snowfall and rainfall velocity. So we no longer use it to tuning parameter. We must model uh, rain and hydrometeor's falling velocity should be closer to the observed evidence. That's one point. So maybe the current model has a kind of compensation errors because the compensation errors, these falling velocity is different, but the model is good. But we should have a different balance between the real falling speed and by changing other characteristics of cloud and turbulences. That's important for modeling community, I think.
Maybe I can comment on that with one sentence. The hydrometeor fall velocity is extremely important to the cloud radiative property. It turns out it's an extremely important tuning parameter. We use that to optimize the current model simulation. So if you can observe that, it certainly helps a lot. With constrained model. I have a question about this. When Satoh tried to compare the different resolution, did you try to retune the model or you stay with the exact same, the parameters, everything is identical except you move toward high resolution? Especially I see you when you, seems like the low cloud distribution, like over the figure, the low cloud change quite substantially from, let's say, 3.5 to 0.44 kilometer resolution. Is this to the like physics, everything is identical, just resolution change, or that also involves some physics retuning?
Yeah, for this line and for this line, we keep everything.
Everything identical.
Yes, that's right.
Okay.
So
And
generally, this resolution is the mean type scheme is preferable, and this resolution is type preferable. So actually, this kind of choice is
maybe
more.
one follow-up. So when you increase horizontal resolution, do you think you might also need to increase vertical resolution? We know stratocumulus cloud is very sensitive to vertical resolution. So as the horizontal resolution get to increased, do you think you
Yeah,
also might need to increase the vertical resolution as well in order to
yeah,
get better?
yeah, you are right. So the next phase or next year, we try to increase vertical resolution. So we hope we increase vertical resolution, we hope more increasingly shallow clouds. So that's my plan.
Thank you very much.
Yeah, thank you. That was a very nice talk and really impressive effort. So I guess you're getting to a scale, a resolution scale here where you can argue it's LES, but a lot of times people are operating more sort of directly in the gray zone. And I'm just curious about, what sort of lessons learned or best practices you might suggest for those who are running, I guess your lower resolution version here where you're sort of in the gray zone of turbulence resolving. Is it simply a problem of interpretation, or are there modeling steps as well that should be accounted for?
Yes, yeah, we are learning from LES people, and I tried gray zone type uh, scheme. But in general, we found a simple LES scheme is better performed in the gray zone area. I mean, the kind of few hundred meters. So yeah, I feel we don't need a complicated gray zone scheme for in general sense.
And sorry, you found that that's best when you turn it on sort of early on when you've entered the gray zone?
Yeah, maybe difficulty to the choice of the mixing lengths. For example, in the vertical and the horizontal lengths are different cases. So maybe we have some choice for the choice of mixing lengths, but generally simpler is better.
I think Surat's question is sort of along the same lines, so I'll read it though. Surat's curious to learn more about the computational performance and the challenges and solutions that you've encountered along the way in getting to such high resolution.
Yeah, the computation performance is briefly written here. Anyway, this kind of simulation can be achieved on more than half of our computer resources used. And this is 8 hours and in this resolution. We want to have a much vertical resolution, but it cannot be possible at current stage. So yeah, just briefly, do you need more information?
So I was curious about like how long did it take for the 8-hour run to finish? Fugaku.
Excuse me, I cannot hear.
How
Oh,
long did it take for the 8-hour run to finish? That's at the 220 meters.
Yeah,
Yeah.
I don't exactly remember, but the kind of kind of week or kind of months.
Months. Okay.
Yeah, actually the first phase, computer is very difficult to run, very I/O problem and the memory problem. So maybe next time I can much easier, maybe kind of week, unit of week.
Yeah, I have
I
a quick question first. On one of your slides, maybe before or after this, you mentioned 400-meter vertical layers. Is that a typo or actually true? Yeah, here. 400-meter in the troposphere?
yeah this is average 400 meters in the troposphere.
Okay, but I believe that for boundary layer, for those shallow clouds, you do need
Yes,
finer resolution.
yes, that's right. In general, in the closer to the surface, we have a finer resolution.
Mhm. And also alluded to what the comments before about the importance of the fall velocity of those hydromedias. They're very relevant to vertical resolution as well, right? You have to the sedimentation you have to calculate from one layer to the other. It travel the whole depth of the layer within a time step or something.
Yeah, I don't think so. In our case, I, I don't think so in general. Some model have such a scheme, but yeah, sedimentation speed is not so fast than the vertical velocity. Maximum is kind of 5 meters per second. So, and in our case, the kind of semi-Lagrangian type uh, scheme is used for the falling ice reinforcing. So, in our case, we don't have time expected dependency.
But your different resolution, you do have different time steps as well, right?
Yeah, time step dependency in general is we should care about. We have here uniformly
Oh, okay.
changing
Yeah.
time step.
Yeah, my general question is about, so it looks like, appear to me, the impression is that you emphasize a lot on the resolution dependence of the vertical velocity. But in general, for climbing model, even cannot resolve those turbulence velocity, not usually is highly parameterized, but the global cloud fraction seems to be still okay compared to satellite or reanalysis. but not those individual events like the hurricane you're comparing to those fine structures the global low resolution cannot capture. But also, it appears to me that the model results are more sensitive to the physics scheme you're using, especially the example you gave, the cloud fraction difference sensitivity to PBL scheme. Could you please comment more on that?
Yeah, of course, any models, low resolution climate model and high resolution kilometer model, physics is important. For kilometer model, cloud microphysics and turbulence model are too important. Of course, radiation also. For climate models, yeah, vertical velocity is not directly calculated in the model. It's a kind of implicit accumulus parameterization assumption. But the sediment falling speed is important for recent climate models are more diagnostic hydrometer rain particles and snow particles introduced, and the sedimentation of these particles directly affect the performance of climate models.
Yeah, excellent talk. And apologies, I can't turn my camera on. I'm somewhere near the New York, Pennsylvania border on I-99 right now. So I had a question. You kind of mentioned this for the end, and this I think follows up nicely on Long's question, where you mentioned that you had been doing a lot of the kind of EarthCARE essentially simulations, synthetic simulations using a single moment microphysics scheme. But then you kind of mentioned the possibility of you were either actively running or testing other, microphysics, possibly like a two or multi-moment scheme. And so my first question is, are the results of the EarthCARE simulations or the kind of the synthetic satellite data that were being used in the EarthCARE planning, is that sensitive to microphysics? And then the follow-on question to that would be, is there hope that data that is procured from EarthCARE post-launch will be able to help better train the microphysics in these high-resolution models?
Yeah, I I didn't catch all the question, but I guess your question. Of course, the model performance depends on the independent implementation of the cloud microphysics and the physics. And the satellite and observation data gives constraint anyway, but there are a lot of observation. We can choose arbitrary observational aspect, but the important thing I think from the EarthCARE is falling velocity, because falling velocity greatly affects the radiation budget of the climate models. So among many observational constraints, I suggest using this falling velocity is most first to look at for the each model, and then try other aspects like size distribution or particle characteristic to tune for the good radiation budget. Then compare, then conduct intercomparison model. At that time, maybe even though my scheme is different, but still that some that variety should exist in the current status.
Okay, yeah, thank you. I mean, I agree. It sounds like this fall velocity is actually kind of a critical constraint, actually. And like I said, Ming maybe was the one that mentioned it about, I know at EarthCARE, this has also commonly been used as a tuning parameter in the microphysics, but in reality, it probably shouldn't be kind of a free parameter. But I'll just finish by saying I'm very much looking forward to, kind of, this is a great example, in my opinion, of using a model to help with like a satellite launch and help with retrieval algorithms. And then I'm really excited to see how the satellite can then kind of feedback and help us improve the models. So thank you for that insight. I appreciate it.
Yeah, thank you, Wes. We modelers should also watch the satellite and new observations. Thank you.
Great.
I agree that we do need this two-way symbiotic relationship or interaction between the models and observations to make it work best. There's a couple, I think, two-ish quick questions, and then I'll turn it over for Ming for like the last question. But the first question is NICOM running on GPUs at all?
Yeah, we are now trying and testing. Currently, OpenACC is used. Not every code is well tuned, but we definitely need to shift the GPU machine.
Okay. And the other question from Robert is, does mixed precision mean 32 and 64-bit, or is there precision lower than 32-bit?
Yeah, we currently use a double precision and single precision two model. I feel half precision is yeah, we want to introduce half precision, but not yet.
All right. So last question goes to you, Ming.
Okay.
Start us and end us out.
Yeah, this is a clarification question. In NICOM, do you have a subgrid cloudiness parameterization turned on, or is a simple or nothing scheme?
Yeah, generally simple or nothing scheme. Yeah, for the
Yeah,
simplicity.
it seems some observations suggest even at this, let's say, 200-meter resolution, some shallow cloud, partial cloudiness still exists quite frequently. So
Yeah.
in that case, might
Yeah.
this resolution, you might want to consider, partial cloudiness. That's typical to GCM resolution. But I guess in a lot of high resolution global storm resolving model, people basically turn off that, just or nothing. I think that potentially could improve the shallow cloud, like low cloud.
Yeah. I understand. I have an option of introduction, but for many reasons, I don't use it. Just switch on and off. Thank you very much.
Thank you very much. Yeah.
Alrighty. Masaki, thank you very much for your presentation. It was very well received. You got us a lot. The panel has a lot to think about now. So let's.
Thank you very much.